Hello everyone, welcome to the next lab of ECE573 Advanced Embedded Logic Design. In this lab, we are going to discuss about the direct memory access and how we can use the DMA functionality to get the data transfer between the different peripherals without the need of the processor. So let's start with the examples of the embedded system deployed in the office security applications. So in this system, at a regular interval, you need to upload the sensor data on the cloud or some memory. So here the data needs to be read from the peripherals and copied to the memory. And another possible task might be to read the data from the local memory and upload into the cloud or the off-chip memory. And as we know that the memory's read and the write operations are quite slow. Okay, it takes many clock cycles to read and write data from the memory, and it is significantly slow when you go for the off-chip memory or the external memories. So this indicate that the processor is occupied during this memory transfer task, and that means processor cannot perform other tasks leading to the poor performance. Okay, so processor has to transfer each byte of data, and that is time consuming process. So during that process, during that time, processor is occupied and it may not be able to process the other interrupts or other tasks as efficiently as possible. So for example, when you connect the large USB or the hard disk to your processor and when you do the large data transfer task, sometimes your processor gets slow or it gets hanged. Okay. One of the reason is that processor is overburdened with the too many tasks. So in such case, why the processor needs to gets busy with the or gets occupied with this memory task? Because what happens in such cases, you have the processor here, say you have the memory here, and you have the peripheral here. So the data is copied inside the say registers in the processor, and from register the data is copied into the memory. Okay, so you can see that the data has to be copied into the register, which is internal memory of the processor, and then it is copied to the memory. So this is the quite a long process. So we need to see if we can do better than this and transfer the data directly to the memory. Also, in many cases, you may have the one system bus, and then the processor has to switch between the instruction phase, data phase task, and that may get delayed over the time. Okay, so to avoid this, people have tried to explore the various options so that how the load on the processor for the memory transfer task can be reduced. One such option is the DMA, that is the direct memory access. So one way of reducing the burden on the processor is to use the direct memory access to perform the memory transfer. So using this approach, processor issues memory transfer request. Okay, processor just say that this is the request for the memory transfer from this source to destination, and this much amount of data to be transferred. Such requests are issued to the DMA, which is the coprocessor or the additional separate unit. So the DMA controller will perform the memory transaction. So here processor doesn't need to copy each byte of data into its local register and then to the memory. Processor just needs to tell the DMA to copy the data from this source to the destination. So what is the advantage? This allows the processor to perform other tasks which are critical while the DMA controller is performing the data transfer. Okay, so Here you can see that you have the processor, you have the DMA, and then you may have, say, peripheral 1 and you have the memory 1, and say this is the system bus. So you can see that this DMA will perform the task directly from the peripheral to memory. Okay, you don't need to have the processor to perform the task. Obviously, processor needs to do some configuration on the DMA to perform at what time you need to do the task. And also, if there is only one system bus, then some bus arbitration is needed so that whenever the processor wants the bus is available. Okay, if there is a one system bus. If there are multiple bus, then the bus arbitration is not that difficult problem. So here you can see that the DMA acts as a both bus master as well as bus slave. Okay, so when it is a master, so for example, suppose that the data is being transferred from the peripheral to memory. So what the bus DMA needs to do? DMA needs to read the data from the peripheral, that is, it is doing the read transaction as a master, and it is doing performing the write transaction to the memory, that is doing the write transaction to the memory. So the DMA controller acts as a master here. Then when it will act as a slave? So when this configuration is being performed from the processor onto the DMA, then it is act as a slave. So the DMA is a unit which can act both as the master as well as the slave. So as a master, the DMA controller communicates with the memory controller while arbitrating for the bus. While acting as a slave, DMA controller sets up the memory transfer by responding to the request from the bus master, that is the processor. Okay, so as a slave, this DMA controller will accept the memory transfer request from the processor, and as a master, DMA controller will perform the transaction from peripheral to the memory, or from memory to memory, or from memory to the another peripheral. Okay, so you can see that the process is quite simple. The first step is that CPU sets up the DMA transfer. Then second process is that the DMA start performing the transfer, and that during that time the CPU is free to perform the any other task. After the transfer is completed, DMA may send the interrupt signal to the CPU that I have completed the task, or the DMA will set up some flags inside its register, and the CPU will poll such flag, and by looking at that flag, CPU will know the current status of the transaction. After the transaction is completed, CPU ends the DMA transfer. Okay, so the process is quite simple, and when we write a code for the DMA configuration, we need to follow this process. So each DMA cycle will typically result in at least 2 bus cycles, either a peripheral read followed by the memory write when the data is being transferred from the peripheral to the memory, or memory read followed by the peripheral write, that is the data is transferred from the memory to the peripheral, depending upon your base address, like depending upon the information you provide to the DMA. DMA controller does not do any processing on the data. Okay, DMA is the only memory transfer. It performs only the data transfer. It does not perform any operation on the data. Okay, it just transfers the bytes as instructed by the processor in its configuration register. So a DMA allows input-output devices to access the memory directly without involving the CPU. Okay, so your input-output like Ethernet, USB can directly send the data to your PL in the Zynq SoC without needing to go through your CPU. DMA permits the peripheral such as UART Ethernet to transfer the direct data to or from memory like on-chip memory, your DDR memory or cache memory or the block RAM memory inside the FPGA without having each byte handled by the processor. So processor doesn't has to copy each byte in its register and then transfer it to the memory. This can be done independent of the processor. DMA enables efficient use of the interrupts, increases the data throughput. So you can see that the CPU can initiate the data transfer request, and then CPU can perform its own task. And once the data transfer is completed, DMA can send the interrupt to the CPU, and once the CPU receives the interrupt, the CPU knows that the data transfer is completed, it can initiate the another data transfer. So in this case, you can see that you don't need to do the polling. You don't need to ask the DMA continuously, okay, whether you have completed the task, whether you have completed the task. The CPU knows that as and when DMA completes the task, he is going to send us the interrupt. So that means that your overall CPU time is more efficiently used and your throughput gets improved. Also, it may lead to the reduction in the hardware cost by eliminating the need of 5 buffers at the peripheral. For example, suppose you have the Ethernet and data is coming from the Ethernet and you want to store into the memory. So suppose that the first packet of Ethernet comes. During that time, if the CPU is busy handling the interrupt or some other task, the peripheral has to buffer that data till the CPU becomes free. Now, since we have the DMA now here, even if the CPU is occupied, CPU can tell the DMA that, okay, these are the packets are coming from the Ethernet, please store it at the particular address. So the amount of the buffers or the temporary storage needed at the peripheral size can be significantly reduced. And as we know that the memories are very expensive and it's an area consuming, so if we reduce the requirement of the memory, it will significantly reduce our cost of the device. But the problem is when there is only one bus and both the CPU and the DMA needs to have the access to the device, access to the bus, then one has to wait for a few clock cycle. Okay, so there is some kind of arbitration is needed because you know that the memory is accessed by the system bus, and if there is a multiple masters want to access the memory, then someone has to wait. So that arbitration needs to be carefully taken into account. So as we discussed, DMA is not intelligent device. It is just a co-processor. It performs the task assigned to him by the processor. So the DMA controllers require the initialization by your software, that is your processor. And what this initialization information include, it is like from your source where you want to read the data, that is the base address of the source. Where you want to write the data, that is the base address of the destination. Then how much data you want to transfer, that is the length of the block. And whether you want to set up the interrupt, whether the processor should generate the interrupt. So there can be a multiple interrupt. For example, whenever you perform the read operation from the peripheral, you can generate an interrupt. Whenever you perform the write operation on the memory, you generate an interrupt. So you can generate a multiple types of interrupts depending upon your requirement. So in a typical DMA transfer, some events such as incoming data available signal from the UART or Ethernet notifies a separate device called DMA controller that the data needs to be transferred to the memory. So CPU tells the DMA controller that this is the memory transfer request. Now DMA controller then need access to your system bus. So what the DMA controller needs? It sends the DMA request signal to the CPU asking its permission to use the bus. So inside the CPU, you will see that there is an additional unit called as the arbitrator, whose task is to understand who wants to use the available bus inside your processor. You can have the one system bus, two system bus, or peripheral bus. So it is the arbitrator is the one who has the complete control on which master can use the bus at a particular time. So the once the request come from the CPU to the DMA that okay, this memory transfer is needed, then the depending upon when source and destination, the DMA will send the bus request signal to the arbitrator. Okay, so it is present inside the CPU. Then CPU, if the bus is being used by the CPU, then it will complete its current activity, then stop driving the bus and returns the DMA acknowledgement signal to the DMA controller. So CPU tells the DMA, okay, now the bus is free, now you can use the bus. DMA control then perform the memory transfer and by driving the address, data and control signal of the bus. When the transfer is complete, the DMA controller stops the driving the bus and deassert the DMA request signal. And then CPU can remove the DMA acknowledgement signal and get the control of the bus. Okay. So you can see that there is a separate hardware module which acts as an arbitrator and decide which master gets to use the bus. Whenever the master wants to access the system bus, you need to send the request to the arbitrator, and once the arbitrator which is there inside the CPU gives the bus access, then you can use the bus. Now arbitrator can decide the bus access based upon the different policies, like you can have the time sharing policy that if you have 5 master, every master will get the access to the bus at the regular interval. But you can see that this is not an efficient, because if this even if the some master doesn't need the access to the bus, he will get the access to the bus and that time will be wasted. So another policy is the a round robin kind of arbitration, where the bus you get the request from the master and you give the access to the bus on the first come first serve basis. Or you can go further that you can implement the priority logic and you can decide based upon the priority who gets the access to the bus. Okay, so there are different policies are being designed for the bus access. Now suppose that the DMA wants to transfer say 1 MB of data. So DMA can perform this operation in a burst mode, that is in a one go you can transfer the all 1 MB of data. Sorry, that is a single cycle mode, that is in a single transaction you can transmit all the 1 MB of data, or you do it in the burst mode. That means you transfer one chunk of data, another chunk of data, and so on. So there are different types of DMA, which some of them support burst, some of them support single cycle, or both, depending upon the how much buffer size is there and what is the capability of the DMA. So in the burst mode, the DMA controller keeps the control of the bus until all the data buffered by the requesting device has been transferred to the memory. Okay, so sorry, I might have missed the discussion in the previous one. So there are two modes. One is the burst mode and the one is the single cycle mode. So in the burst mode, your DMA controller keeps the control of the bus till it transfer all the data. Okay, so that means what will happen, suppose you are transferring 1 MB of data, and at a time you can transfer say only a few KB of data. So until you transfer all the 1 MB of data, you get the access to the bus. In single cycle mode, DMA controller gives up the bus access after each transfer. That means what happens after suppose you are transferring 1 MB of data and you can transfer say 4 KB only at a time. Then after every 4 KB transfer, DMA controller gives the access to the bus to the arbitrator and then send a request again that I have the additional data to be transferred. Please give me the access again. So in case of the single cycle, the only one data transfer is completed and then you get the access to the bus back. So the single cycle mode minimizes the amount of the time that the DMA controller keeps the processor off the memory bus. Like in the single cycle bus, you know that after the deterministic time interval, you are going to get the access to the bus. That processor is going to get the access to the bus. The processor performance does not get affected. But you can see that there is a lot of handshake needs to be done with the arbitrator to give the access back to the bus and to gain the access from the arbitrator. So this obviously results in the overall system throughput if the lot of data needs to be transferred. Okay, so that is the drawback is there, but at the end you don't want your processor to gets affected because of the DMA. So in most of the design, usually we prefer the single cycle mode if your system cannot tolerate more than few cycles of the interrupt latency. For example, if you keep the processor off the memory bus, then it will significantly affect your interrupt latency, because to process the interrupt, you need to execute the particular code ISR. And if you don't have access to the memory bus or the memory, then your execution of the ISR will get affected. So with the burst mode, there is a chance that your interrupt latency is will get significantly affected. So for the application where the interrupt latency is critical, you use the single cycle mode. Also, the burst mode may be used by the peripheral and by the malicious peripheral to keep the processor off the memory bus. For example, a peripheral device can buffer a large amount of data, causing the DMA controller to tie up the bus for an excessive amount of the time. Okay, and this may lead to the system failure. In this case, single cycle mode is preferred. Okay, so these are the modes of the DMA. In case of the Xilinx DMA, we have the two more modes, two different types of the operations also. That is called as a scatter gathered operation or the simple transfer operation. So in case of the simple transfer is the one. In case of the simple transfer, so what happens, suppose this is your source and this is say bunch of data you want to transfer, and this is your destination and you are going to transfer it here. So the amount of the data you transfer is the contiguous data. Okay, so it can be, it is, you just need to provide the start address and the length of the data. In case of the scatter gathered mode, it's a scatter gather mode. So in this case, your data is divided into the multiple chunks. So you can see that here you have the two sets of data and you need to transfer at this location. So here you can see that you need to provide the two start address and the length and the two destination address. And this is done using the scatter gather. So you just need to send one request to the DMA that I have these two chunks of data and to be transferred at this destination. And then in this case, you need to configure the DMA in the scatter gather. While in case of the simple transfer, you just need to transfer the one bunch of the contiguous data from source to destination. Okay. So in case of the Zynq SoC, what we have seen that there is a DMA inside the processing system that is called as a PSDMA, and this PSDMA can perform the data transfer from the DDR controller to the peripheral or FPGA or to the on-chip memory. So we have seen the various data transfer in case of using the DMA. So we have discussed that how the DMA can do the memory to memory, like on-chip memory to the DDR memory, or memory to the PL, or PL to the on-chip memory type of data transfer. While in this lab, we are not going to use this DMA because we are not using the ARM controller. What we are using is the microblades, which is there inside the FPGA. And to inside the FPGA, you may have the block memory, okay, and you may have the peripheral. So if you want to transfer the data between this one, you can use the DMA, which is there inside the PL. Okay, so we are in this lab, we are going to discuss the such kind of DMA which can enable the data transfer between the block memory and the peripherals. So if you see the catalog inside the Vivado, you will see that there are different DMAs are available. Like this is the central direct memory access. This is CDMA. This is the data mover. This is the DMA. So data mover is a simpler version of the DMA. Then you have the multi-channel DMA. So you can perform the multiple transfer simultaneously. And then you have the video DMA. So if you want to do the 2D transfer, you can use the video DMA. So there are small difference. So you can look at the data set to understand what is the difference between them. In the today's lab, we are going to use the direct memory access. So here the CDMA, it can be used whenever you want to transfer the data from one memory to the another memory. Okay, so CDMA perform the transfer between the memory map source address to the memory map destination address. Okay, so if you have the IP which has the stream interface, you can't use the CDMA. If you have the IP with the memory map interface, then you can use the CDMA. Okay, while a DMA, as we have seen when we discuss about the AXI stream protocol, DMA IP will help you to transfer the stream interface to the memory map interface and the memory map to the stream interface. So as we discussed, if you want to write the stream data into the particular location into the memory, you need the stream to memory map conversion, and that can be done using this DMA. And the video DMA, as we know, it is the used for the 2D data transfer for the video and image processing. And then you have the data mover, which is similar to the DMA, but it's a smaller, less complex version. Like it doesn't support the interrupts. It has the limited capability compared to the DMA. Okay, so you can use the DMA or the data mover to get the desired task. So this completes the theory about the DMA. Okay, so now we'll go back to what we are going to do in the lab. So in the lab, we are going to build the block diagram, which looks something like this. So here you can see that this is the microblaze, and this is your DMA, and this is your signal processing IP. Okay, this part is the homework part. Okay, so this will be as your lab homework, which the videos are already uploaded. You can look at those, how to do that. So in this case, you can see that what we need to do, we have the microblaze. The microblaze will write the data to be processed inside the block RAM. Then this DMA will read the data from the block RAM, send to the IP, and the processed data will be sent back to the DMA, and DMA will write the processed data back to the block RAM. Okay, so what is the first task? First task is the microblaze needs to write the data to be processed inside the block RAM. And how it is done? You can see that on the microblaze DP port, we have used the interconnect. Okay, this is the AXI interconnect. And using the AXI interconnect, your microblaze is the one of the master, and your slave is the block memory. Okay. Now in the block memory, this is your IP of the block memory, but it doesn't have the AXI interface. Okay, it is a non-AXI interface. For example, you have the address port, write enable, read enable, data port. You don't have the AXI port. So to enable the AXI devices like microblaze or Zynq to communicate with the block memory, Xilinx has provided us the AXI BRAM component. So it receives the AXI transaction and it converts into the transaction which can be understood by the memory depending upon the read and the write transaction. So this DP port, through this port here, you can perform the write transaction at the particular location inside the block RAM. So now the microblaze has written the data inside the block RAM. Now what the next task is that microblaze needs to configure the DMA. So if you see this DMA, you have this SAXI light port. And as we have discussed in the beginning that these light ports are used for the configuring the IP in the FFT or the DME. So via this light port, the The microplace configures the DMA, tells the DMA that from this block RAM, from this address, takes the data, pass this data to the particular address, that is a destination, and then receive the process data and write back to the at the particular address. So this configuration is done by the AXI light port on the DMA via microplace. Okay, so we have prepared the data to be processed in the block memory. We have configured the DMA, and now the next thing is that we need to connect our IP to the DMA so that the data transfer from the IP to the DMA and from the DMA to the IP takes place. Now, let's spend some time on the various ports of the DMA. So you can see that this light port we have discussed, this is used for the configuration. Then there are two MAXI port and the two MAXI-S port or SAXI-S, that is a two stream ports. Okay, there are two stream ports and the two memory mapped ports. Okay, now let's focus on the memory mapped ports. So you can see that these are the two memory map port. Who is the master on this one? Your DMA is the master. And you can see that the first port is the MM2S. So what it does, it reads the data from the block RAM and convert into the stream interface. Okay, so this is the one. And this is the second one is the MXI S2MM. What is the S2MM? It does the opposite task. It takes the data from your IP in the stream protocol and converts into the memory map so that it can be passed to the corresponding block RAM. So now you can see that where these ports will be connected, these ports will be connected here, interconnect, so that the DMA is master to the interconnect and so that it can write into the memory. Okay, so that's why these ports are used. So these ports are used to read the data and write the data from the memory interface. Now look at the stream. You have this one and this one. The first one is the MAXI-S MM2S. So what it does, you have received the memory map data from the block RAM, you convert into the stream one and you pass to the you pass to the IP. Okay, so that is what you are doing. Then here you can see that slave AXIS S2MM. So here you have received the data from the IP and you convert into the memory map. So you can see that this data will be passed here. No, sorry. So this is MM2S. So this data will be passed here and this data will be passed here. Okay. So you can see that now just focus on this part. Okay. So you can see that the SMAXIMM2S, this data is being passed here. Your IP is doing the operation and then this data is being passed from the IP to the DM. Okay. So this is being highlighted in this one. So what I'm doing, I'm taking the data from the block RAM. I'm here, what operations I'm doing? I'm getting the integer data from the block RAM. So suppose that I'm getting A is equal to say 4, 9 and 16. Then I'm converting into the float format. So it will be A is equal to 4.0, 9.0, 16.0. Then I'm calculating the square root. So it will be 2.0, 3.0, 4.0. And then I'm doing the accumulator. So this is the part of the homework, which we are not doing as a part of the lab, but you need to do it as a homework. So here A is equal to 9. Okay, the output will be here 9. So you can see here. So you can see here that just wait a second. Okay, so your output will be passed to the IP. So you can see that these IPs I have these two IPs we have used directly from the IP catalog, and in this IP we have generated via HLS and we have exported to the IP catalog. So corresponding video is already available. You can watch the video. Okay. So now the last part. Okay, so this is how the DMA is communicating with the block memory. So this is your block memory via using the MM to S port. You can see that via this port, DMA is copying the data from the block memory, and via using S to MM port, DMA is writing the data to the block memory. And then the last step is the writing the software. So writing the software is quite easy. It's not that complex. You have this input data, and here you are writing the data into the block RAM. Okay. So this is the data I want to process. I'm using the base address of the block RAM. I'm using this function to write the data at the particular address and the corresponding data. Okay. So you can see that since each data is 32-bit and your address of the block RAM is byte addressable, so I'm increasing the address by 4. Then the next step is the configuring the DMA. So you can see that there is a certain steps needs to be followed for the DMA configuration. Again, via in the .h file, the process are given. So there are two structures are there in the DMA compared to the one structure in the other IP. One is the configuration structure and one is the DMA structure. So by using the base address of the DMA, you find out the, all the details of the DMA configuration structure. Then you do the initialization of the DMA. Then you initiate the two transfers, one from the DMA to the IP, second from the IP to DMA. Okay, so here you can see that the this is the direction. Okay, so this is from the device to DMA. So your DMA is receiving the process data from the IP. Again, you can see that the what is the start address. This is the my base address and 8 into the this one. So you can see that this is my block RAM. So initially I'll store 4, then 9, then 16, then 28, then 40, then 55, then 76. So this is my initially where I will be storing the data, and my process data will be started from this one. So I have added 8 into the size of int, so to the base address, so that the data which will be received from the IP will be stored from this location onward. Okay. So, and there is another transfer called as the DMA to device. So I'm data which is written into the block RAM by the processor, I need to send to the IP. So you can see that here what I'm doing. This is the base address, that is the initial address, how much amount of data and in which direction. So once I'm done, so I have initiated the transaction, I need to check whether the transaction is completed or not. So inside the DMA, there is one status register, okay, and the 0th bit of the status register, okay, is used to see whether the DMA is in performing the task or it has completed the task. Okay, it's a halt flag. Okay, again, these are the information which you will understand when you read the dataset. For now, for our labs, I'm giving this information. Okay, but feel free to look into the datasheet. So what we are doing, we are reading that register. So when this register is present for every direction, there are two registers, separate register. So for one direction, you have the register at the 4th address, and the second direction, you have the register at the 34th address. And each register is 32-bit. So you get the 32-bit of data, and you need to take only LSB. So you multiplied with this mask. This mask is nothing but the if you consider the hex, it is nothing but the 001. So it will extract the LSB bit by doing the AND operation and will check it as a status. If this status is equal to 1, that means DMA has completed the operation. If it is not 1, that means DMA is still doing the transfer. So we'll check it for both the one from IP to the DMA and DMA to IP. When both are completed, that means our transaction has been completed. Okay. So this code is again discussed in the video and in detail, and also we have explained the corresponding simulation results in the video.